as mathematical structures, but rather model systems representing the former. Hence, many mathematical structures that we find in economics are not instantiated by target systems, but only by model systems obtained out of idealized conditions. It is usual in the process of elaboration of economics theories, the construction of ideal objects out of concepts that, even though they originate in experience and correspond to real properties of real beings, have suffered a sort of deformation. For example, there is no doubt that real economic agents are human beings who handle certain information, who can remember events, and that can also perform arithmetic operations. That is why the predicates 1, 2, and 3, X possesses information, X has memory, X is able to perform calculations, are true of human beings who effect economic transactions anywhere. Nevertheless, even though economic theory has to refer somehow to the properties they denote, the use of mathematical method requires the use of deformed versions of such predicates, or of the concepts they express thereby. Some specializations of economic theory require, for instance, for the economic agents to possess perfect information, perfect memory, and unlimited computational powers. Thus, for instance, predicates 1, 2, and 3 are deformed in order to obtain 4, 5, and 6. X possesses perfect information, X has perfect recall, and X has unlimited computational powers. The conjunction of predicates defines a type of ideal object, what we have called a model system, non-existent in reality, but required to channel mathematical reasoning. As Walras put it in Elements d'économie politique, the mathematical method is not an experimental method. It is a rational method. The pure science of economics should then abstract and define ideal type concepts in terms of which it carries its reasoning. The return to reality should not take place until the science is completed, and then only with a view to practical applications. Let us call idealized concepts or idealizations the concepts obtained by deformation out of concepts which are truly predicable of real beings. If in spite of this deformation the same are meaningful, even if they are false, of these real objects, and keep an intention akin to those, we have called ideal objects those model systems built by means of conjunctions of predicates that express idealizations. The actions of a consistent economic theory define directly as a theoretical predicate, as A is a regular preference structure, but they are also obliquely true, at least under a typical interpretation of the primitive terms of ideal objects. For instance, the just mentioned predicate can be defined canonically as follows. A is a regular preference structure if A is a weak order. It is debatable whether the preference relation exhibited by a human agent at a given moment is connected and transitive. Nevertheless, the systematic development of the theory can go on as if it were so. Utility theory has proceeded through the construction of ideal objects endowed with idealized properties. It has assumed, for instance, that the consumer, an ideal object, defines his preference relation over a space of consumption menus, which is representable as the non-negative orthon of RL. Other idealizations introduced over and above these are those of a continuous or unsubstantiated preference relation. All these idealizations are needed in order to prove the existence of utility functions possessing certain characteristics required by economic theory, like continuity or monotonicity. Hence, the use of RTM to obtain such functions cannot be seen as a case of empirical measurement. It is usual in economics the application of RTM methods to obtain representations of idealized magnitudes. For instance, Bieber and Dembski used such methods in trying to fundamentally measure income. They found that income can be fundamentally measured only in a world of complete and perfect markets. but not necessarily otherwise. They concluded that at a fundamental level, the central feature of financial reporting cannot be income measurement. Let me skip this section. And let me finish by talking about models of data in measuring procedures. The view of theories as systems of set theoretical structures naturally leads to a particular view of theory application and testing. Typically, to conceptualize a certain phenomenon means to apply the conceptual apparatus of the theory, fleshing out the terms with a particular concrete meaning. For instance, in order to conceptualize a target system C, a real human consumer, demand theory claims that C be represented by a certain model system M, which is a consumer with unlimited memory that knows beforehand what would be his election in confronting any budget set. The information of this ideal consumer is represented in a set theoretical structure by means of a demand function, eta. If the Slotsky matrix corresponding to eta is symmetric and negative semi-definite, M knows that eta coincides with a Walrasian demand function mu derived from a utility function that represents his preferences. Moreover, since M has unlimited computational capabilities, he can determine instantaneously the preference relation from which mu, which turns out to be eta, derives. Now, if the theory represents C with M, the scientist may try to apply T to C. Whether T is applicable or not to C is an entirely empirical matter. To say that it is a claim, to say that it is a claim that has to be held on the basis of empirical data. Varian has stressed that there are two approaches to this problem. One, the approach based upon calculus, originated in the work of Antonelli and Slutsky, derives necessary and sufficient conditions on the derivatives of the demand function eta. The second, originated in the work of Samuelson, is called non-parametric because it assumes no specific form whatsoever for the demand function. The distinction between the two approaches is very important in empirical work. The calculus approach assumes that the entire demand function, that is to say our eta, is available for analysis, while the algebraic approach assumes only a finite number of observations on consumer behavior is available. Since all existing data on consumer behavior does consist of a finite number of observations, the later assumption is much more realistic. Now, we can explain the non-parametric method by means of the concept of data structure, or as Pat prefers to call it, model of data. Observing the behavior of the agent, we get the structure of data that you see here, with a eta with a hat on top, where such eta is a function defined over a finite subset of price cum wealth, precisely that of pairs of systems of price and income levels under which the behavior of the consumer has been actually observed. The empirical demand function eta hat is obviously finite and discrete, which is something that Pat loves a lot. Finite and discrete things that can be observed. And this is why structure D can be depicted by means of the table. This is here. That is the structure, completely presented. Now, the non-parametric method does not try to build directly the complete demand function eta, but rather uses an algorithm to build directly a utility function that rationalizes the data, provided that structure D satisfies the conditions of the following theorem, using Afriat. You can see the conditions. Basically, is the data satisfy the general action of revealed preference, and that is equivalent to all the other conditions. In particular, the existence of a concave, monotonic, continuous, non-associated utility function that rationalizes the data. Afriat and Varian provided algorithms by means of which it is possible to build a utility function U that rationalizes the data of structure D. This is jumping, so to say, from a model of data to the theoretic function U, utility. Then it is possible to embed D in the partial structure consisting of the Walrasian demand function mu induced by the utility function. That is to say, mu restricted to F coincides with eta hat. The parametric method, on the other hand, tries first to determine the non-theoretical demand function eta without involving the utility, and afterward tries to recover the utility out of eta. The upshot, and I'm finishing now, the upshot of this example is that there are some applications of economic theories that require methods other than those of representational theory of measurement in order to flesh out the terms of the theory, to actually measure the magnitudes referred to by the terms of the theory. Suppes himself used methods more similar to this, fleshing out the magnitudes out of models of data in his classical experiments on learning theory. Hence, more than a method to flesh out the terms of a theory and empirical application or testing, I think in economics the representational theory of measurement seems to be rather a methodology to establish the existence of metrizations, sometimes even for idealized magnitudes, and especially for this. But thank you very much for all you have given us, and have a happy birthday.